corrosion, and like development of various protective coatings. In addition to this, we do other works, like especially the consultancy services for various organizations like NTPC, IOCL, BPCL. So when they face a problem due to corrosion, so they invite us and we used to go there and we used to check why the corrosion is happening and what are the root causes for the corrosion and related failures and what are the mitigation measures, and we used to recommend those things. In addition to that, we at SECRI, our lab, especially the protective coating group, we used to test various paint schemes developed by other manufacturers like Hempel, Asian Paints, and Nerolac and Sai. So whatever the paints they develop and they used to send to us for testing. So we used to test based on, a project basis, and we used to give them the report. These are the various activities we do here. And then another important thing, I don't know how many of you are aware of this. SECRI used to make this corrosion map of India. So what we'll do, we will, keep various materials depending on their location and corrosivity, and like steel and especially carbon steel, the mild steel, and the zinc and aluminum and galvanized iron will keep on different places, and we'll find out the corrosion rate for 2 3 years 4 years. Then we'll find out the rate and then we'll make the map. And currently this map updation job is under progress, so the updated map will come soon with the funding from CSIR. So before going to the corrosion protection, we should know about corrosion. So we know that, we all of you know that uh, corrosion is, we cannot avoid corrosion. We can't stop it because it's thermodynamically the inevitable process. So we used to get whatever the materials and the things which we require through the mining and extraction melting. We'll get the alloy making process and then work on machining, and we will get design shape. And then when it is in under operation, it undergoes corrosion, then go back to the initial stage. This is a cycle, a corrosion cycle of materials. And then how can you define corrosion? So if you do the definition of corrosion means, we can say that when a material is interacting with the environment and the degradation happening to the material and the material is losing its useful property, so we can term it as a corrosion. So we generally, the corrosion manifests as the loss in appearance and the loss in load bearing ability. So it can be physical and the chemical and electrochemical. So as I told in the earlier thing, thermodynamically, we cannot prevent it. Only we can stop to some extent by using some measures like the proper design of the material and structure, or by choosing the correct alloy for the environment whichever you require. And after doing both these things, you can go for a coating and you can use some kind of inhibitors, or you can do cathodic protection. So I told you that, the corrosion is having the electrochemical nature. That means, generally we use study that we need to have an anode and cathode, and then the oxidation happens at the anode, and electron get produced and move to the cathode, they get consumed. And local anode and cathode can be there on the same type of metal also, due to some difference in surface energies, grains and grain boundaries. Grain boundaries will have a higher surface energy, so they act as the anode, and the grains will act as the cathode. So differential, the electrochemical cell will form there, so corrosion can freely happen. So this is the we'll come to the electrical double layer. So this is what many of you may be knowing about this one. So here, when I'm putting a metal in a solution like electrolyte solution, suppose NaCl solution, what is happening at the metal and the solution, the electrolyte interface, or the electrode-electrolyte interface? Various models came. Initially, there was a Goy-Chapman model. So why I'm discussing here, the coating plays a role in this electrical double layer. The electrical double layer will change when you apply a coating here. So suppose this, when you put a metal surface in a NaCl solution, you can see that, here you have the positive charge on the metal surface. Goy-Chapman told that the solution side will be a diffused layer will be here, and the negative ions here will partially cancel out the positive charge here. And when come back to the Stern model, he told that you have a Goy-Chapman diffuse layer is available here. At the same time, some of the anions are attached to the metal surface. And the later come the latest model, that is a Bucris and Devnathan and Muller model. And this model actually explained uh, this model explained that it is similar to Stern model. There are two differences. One, the instead of the negative ions coming and sitting at the electrode interface, the water dipoles are coming here, layer of oriented water molecule with the negative part of that moving facing towards the positive charge. And then here you can see some of the chloride anions. Suppose in the NaCl solution, we'll have a competition between the water dipoles and chloride anions. Some area the chloride anions will be sitting. And then here after that, there will be hydrated cations will be sitting. And this is the inner Helmholtz plate and the outer Helmholtz plate. This is a typical how a electrical double layer looks like. So when you go, how this double layer is, what is significance of the double layer to corrosion? So you can see each of this double layer can, we can model as a parallel combination of a capacitance and a resistance. And this RP is inversely proportional to the corrosion rate. So if you have a coating, if you apply a coating, how the things will change. So in this figure, you can see the first image, this part of the image, this is a metal and electrolyte. Here there is no coating, but here there is a coating is there. So here you can see the large electric field. Actually, in this area, you can see this small area, the electric field will be of the range of 10 raised to 7 per centimeter, because 1 volt only, but the narrow region, that region is very narrow. This region is very narrow in 1 angstrom only. That's why you have a very high electric field. So here metal dissolution will happen. At the same time, when you have a coating, the presence of a further diffuse double layer due to the coated area. So inhibition of metal dissolution takes place due to slow electrode kinetics. So now we go how a coating is protecting a substrate from corrosion protection. So there are various mechanisms. First of all, one can say that basic barrier protection, that is the complete isolation of the substrate from the environment, that it acting as a barrier for any ions which is coming or water molecules, whatever through the, it should come through the extended diffuse double layer of the coating. Then the adhesion of the coating, that is another thing. There are two types of adhesion. That is, one is a dry adhesion, wet adhesion. When you apply a coating, it may be adhere. We find that it is good adhesion is there. But when you're depositing, keeping that coating in a aqueous medium, water or a water at 40 degrees Celsius, there is a SPM test for to find out the water resistance and adhesion of the coating. We can find that the coating does not have enough wet adhesion. Then it is blocking the ionic paths between local anodes and cathodes along the metal polymer interface. Then another thing is the chemical inhibition. That means we'll add some kind of inhibitor molecules in the coating so that they will stop the corrosion. Then another one is this galvanic protection. Coating with more active metals. That is, we know that the galvanized ion, zinc we will use. Zinc is more active, so zinc will undergo corrosion, protecting the underlying the ferrous metal substrate. So these are the a major way how a coating protects underlying metal substrates from corrosion. So if you see coatings, the coatings are everywhere, whatever, if the mobile phone which we are using, they have kind of anodized coating, and in our home, we have the architectural coatings and the bridges, everywhere we can see coating. So it is having the functional and decorative requirements, and its application span, very wide applications. But if you see the coating science as a field, it's a very old field, but not a mature one. The one problem which faces the coating science, the field, is that suppose if I make a new coating, tomorrow immediately I cannot go to the market. Because how can you say that your coating is having a life of 10 years and 15 years? We need to do research. Minimum of 3 to 4 to 5 years required to have a proper, coating development, from the starting from the raw materials to the formulation to the testing and standards, and then certification, and go back to the industry. So it will take time, because we can't actually keep a substance all the time in the atmosphere, natural atmosphere, to do whether it is working for 1 year or 10-year kind of thing. We have accelerated testers that has to function minimum of 2 months or more than that. Then only we can extrapolate that to 10 years or 15 years like that. So there are a lot of R&Ds happening to understand various scientific understanding. And the coating developments, another thing is R&D is happening is to reducing the emissions. Like, if you see as an industry, the coatings and paint industry is second to gasoline industry for contributing to the greenhouse gas emissions. So especially the solvents. So when you enter inside a newly coated room, if you're getting some nice aroma, means that is nothing but the solvent which is slowly being evaporated from the coating. So we need to reduce those emissions. So there are requirements for high volume solid coating. That means the coating which is having solid content more than 8% when you get the dried film, and then reducing the other energy requirements, and finally combating corrosions. So these are the recent development happening in the coating world. So if you see by appearance, you can say that a coating can be clear, because in most of our car coatings, we give top coat will be a clear coat, and then can be pigmented, glossy, and metallic. And functionally, if you see, some of the coatings are anti-corrosive coating, anti-fungal coating, and some application you require abrasion resistance and skid resistance, can be decorative and can be photosensitive. So for example, in the case of a conventional coating, it just acts as a physical barrier. That means it separates the substrate from its environment, and it is having only a passive protection and decoration only. But you can see a coating's functionalities and properties can be modified based on some kind of additives, or you can do a kind of functionalization of the coating matrix. So they call a kind of multifunctional coatings. That means a coating can be at the same time hydrophobic, self-healing, anti-corrosion, antimicrobial, and photoluminescent. So what we will do actually, if suppose the substrate and the coating and can add some kind of additives as I mentioned, and these additives can be anything, and we can discuss in detail about these additives in the coming slides. So how can you say your coating is smart? A smart coating will be a coating that can sense and respond to a stimulus in its environment, like for example, pressure, light, heat, etc., and react in a predictable and possibly in a reversible fashion. So if a coating satisfies these criteria, the coating can classify as a smart coating. This is actually in a smart coating third conference in February 2011. Professor Jamil Baghdadi, he offered this definition, that is the materials that are capable of adapting their properties dynamically to external stimulus are called responsive or smart coating. So the term smart coating refers to the concept of coating being able to sense the environment and make an appropriate response to that stimulus. So this coating can be termed as actually a functional or multifunctional coatings also. So what is smartness of a coating? So the thing is that is smartness of a coating limited only to the cured state, or it may be in the formulation stage? Smartness of a coating may also exist in the formation of a coating rather than its cured state also. Formation of a coating means there are this kind of self-stratifying coating. When you apply it's only one coating only, but when it's forming in the layer, the cured state, you can have a two layer based upon the densities. Okay, so there are kind of a self-stratifying coating that is also being developed. And in designing a coating, the chemical nature, the surface energy differences, and the relative reaction rates of the coating ingredients may be selected so that the final cured coating has a specific functionality at the surface. This is what I told, self-stratifying coatings. This is what. And then, regardless of the definitions, the smart coatings field has explored with new developments and materials, because people are exploring with various materials, new materials, what is happening in the material science. Okay, when you have a new material like graphene, when came, people immediately took the graphene as a filler or a pigment to the existing coating and try how good they are. Then comes the emaxines. Recently emaxine, another brand of material, so people are nowadays using emaxines as a coating filler. Then the hexagonal boron nitride, the white graphene, so and then clay nanoparticles. So these new materials, okay, they're just coming and they're adding to the formulators toolbox as a newer materials. If you see, virtually any typical coating formulating ingredient can be used to make a smart coating if applied appropriately. This is one of the important things why I've told if applied appropriately. So you can add anything for the case of graphene or carbon nanotube. Sometimes if you see the formulation stage is not that easy stage because it takes a lot of time. A lot of permutation and combination can be done. Maybe if you add more than 5-8% of graphene or some other novel additive, the other property of the coating will be antibody. So we need to keep in these things in mind because the most important thing of a coating, it should act as a barrier. When the coating is failing to act as a barrier, then whatever the smartness you are adding to the coating of no use actually. Okay, so that is the most important. So whatever you are adding, it should not affect the barrier property of the matrix. And then certain materials have emerged recently that are particularly useful in providing increased functionality, often when used in relatively small amounts. Most of the recent industry things and papers, if you see the graphene or a carbon nanotube, they should add in a very small quantity like 1 weight percentage, 2 weight percentage. And then most of things are these are known as nanomaterials, but there are problems when you use nanomaterials in a paint formulation that we will see later. For example, right now people are using carbon nanotubes and the clays, various nanoclays are available, and UV screening particles like titanium, cerium, and zinc oxides. These are many emerging nanomaterials which are being used in the coating. And then you see, if I use nanomaterials in coating, how it is the betterment of using that. For the image, you can see the first one, I'm using a micro scale particle, the second one, nanoscale particle. You can notice that if you are finely disperse these nanoparticles in the coating, if you have, that's what the better dispersion is very, very important throughout the filling. This particle can be more effective than the same weight of micro scale particles if they are sufficiently applied here. And then the carbon nanotube. The carbon nanotube, it improves the conductivity of the coating. So the application of the CNT, especially coming carbon nanotube and the graphene, is that especially for a zinc-rich coating. The zinc-rich coating is the one of a traditional coating which have been using for protecting the industrial paint scheme. Zinc-rich coating of around 75 to 80 micron thickness. And the criteria is that for a zinc-rich coating to be protect the underlying surface to cathodically, it should have minimum of 18 weight percentage of zinc in the dried film. So it's large amount of zinc you are being used here. At the same time, it was found that out of the 80 percentage during the lifetime of the coating, only 60 weight percentage or 55 weight percent of zinc is being used. Remaining is unused. So you're wasting a lot of zinc, and the zinc is sometimes being released aquatic system, and it is affecting the aquatic life also. So you can add some kind of fillers to reduce the amount of zinc in the coating, but at the same time you cannot add any kind of fillers because the filler should be conductive. The filler should be conductive to maintain the electrical connectivity between the each zinc particle and the zinc particle to zinc particle to the iron particle. So carbon nanotube finds a good application in this formulation. So various things are available now. And all these smartness of the coating, the start using different kind of material started from here, the chromate conversion coating. So for aerospace industry, especially aerospace industry, aluminum is a material they are using because the weight is more important than the aerospace. You can't use steel there. Okay, so aluminum, we know that we have the aluminum oxide film will be there, but it's very easily undergo corrosion in the alkaline, in environment containing chloride ions. So it undergo pitting corrosion, localized corrosion, and filiform corrosion. So it's a big problem. So to avoid that, people started using the chromate conversion coating. And this chromate conversion coating, now also I would say the chromate, one of the things the industry industry wants to replace it, but yet to get a proper replacement for a chromate conversion coating or a chromate pigment in the coating, because the chromate actually protects by two methods. One is a physical barrier. So it will have the both CR3 plus and CR6 plus in the final coating. The CR3 plus is actually insoluble and it will acting as a physical barrier. At the same time, this is most important, the active corrosion protection. That means the coating is having a CR6 plus. So that CR6 plus actually can leach and it leach in the coating and it will go to the area with the damaged site and it prevent further corrosion there by making a film there. So this is one of the important property, the self-healing property of this chromate layer when you are acting as a conversion coating or when you add zinc chromate or strontium chromate as a pigment in the coating. So this is one of the most important thing for the chromate conversion coating. So most of the research happened for the last 50 years in the coating I mean, industry or the academia is that how to replace this chromate conversion coating. So all those smart coatings, as far as the corrosion protection concerned, actually started to replace this chromate conversion coating. So I told you one term called active corrosion protection. Now, if there is an active corrosion protection, then what is the passive corrosion protection? If active, there should be something called passive also. The passive is actually the barrier protection. That is the coating just acting as a barrier between the metal and the surrounding. When the barrier, something happened to the barrier, it's gone because the ingredient, I mean, these corrosive species have direct access to the metal. So the active corrosion protection is that it decreases the corrosion rate when the main barrier, the main coating matrix is damaged and corrosive species come in contact with the substrate. So barrier property breaches, then a protection is comes into play. That protection is known as active protection. The coating should provide release of the active and repairing material rapidly when coating integrity changes. A kind of self-healing. So, how can you define self-healing in corrosion? We can say the self-delaying and protection from corrosion activity of a defect causing corrosion in a coated material by any mechanism can be considered as self-healing. That means if you see coating here and you added some kind of nano containers here and the nano container may have some kind of stored inhibitor or some other chemicals. So when a corrosive ion attacks or a defect came here and ions are coming here, in the presence of this corrosive ion and the entry of the corrosive ion is acting as a stimuli and the container is breaking and with the stimuli and this inhibitor or something is coming out and here leaching is happening out and a film is forming and stops further corrosion. This is actually the idea of self-healing in corrosion. And I told you generally two ways you can do that. One is that you can directly add a kind of inhibitor into the direct coating, and the image you can see this is a undopped sol gel coating. This is a dopped sol gel coating. Dop means you added a kind of benzotriazole here. So what is happening when you're directly adding the additives into the coating? We found that actually the benzotriazole will have some negative effect on the barrier property of the matrix itself. So it is degrading the barrier property itself. So in order to avoid that, sometimes undesired leaching will be of these inhibitors will be there. So in order to avoid that, what we can do is we can load these inhibitors inside the some containers or some reservoirs and add here. So by encapsulating, what you can do is the leaching to the environment is reduced, unwanted leaching is not there, and there is no unfavorable interaction between the active species and the coating matrix is not there, and you will have a stimuli triggered release as and when required only, and localized release will be there and prolonged protection will be there because there is no unwanted leaching and no deactivation of the active species, and it can have both the active and barrier protection. So, if you see the present status of self-healing coatings, two kinds are there. One is at the structural level and another is at the functional level. So there are three schools of thoughts here. So structural level is level mean for example the classical concept of a material science. That means the complete recovery of the structural integrity of the coating. Suppose if I made a scratch on the coating, so the scratch is completely healed. And the functional level, what they're talking is actually the recovery of the major function of the coating. For example, the coating The major property of the coating is anti-corrosion. So that is the property, anti-corrosion property. So when due to some defect or some other happenings occurring, the coating is undergoing corrosion, the corrosion stops there. But that the defect is formed, but the defect may not be cured physically, but the problem of corrosion stops there. So there are two types of things here. One is polymeric based coatings. So here a monomer and catalyst is added into the coating. When the integrity of the coating lost, the monomer undergo polymerization and heals the defect. Here, inhibitor loaded nano container mixed with sol gel based protective coatings. When corrosion starts, inhibitor gets released from the container and delays corrosion. So we will see both things, but I will speak more about this functional level only because my research mainly focusing on the functional level, on the structural level. Because structural level, there are a lot of problem as far as the scaling up is concerned because various things are involved here and cost is also one of the factors here. Now, a structural perspective, all these things starts with this paper in February 2011, which is Nature. That is the paper published by the from USA, Urbana-Champaign University, Illinois, in USA. This paper is one of the autonomic healing of polymer composite. So what they made is actually in the coating they made these capsules. These are microcapsules, okay, and there is a healing agent inside the microcapsules, and these are the catalyst. So when the healing agent comes, there is a polymerization will takes place with the matrix and the healing agent in the presence of this catalyst. This is what they envisaged. The same group later developed their work further, and I can show you this article came as a cover page in Advanced Materials in 2008 or 9. 9. And you can see this is a coating. They made a scratch here. This is a HCM image of the scratch. And when the healing happening, you can see the depth get decreased, but not complete recovery, but something recovered here. And electrochemically also they proved that, you can see that this is the current we are getting in the control sample that is here. But when it is healed, you can see it is come down. The current is less here. Okay, this is the mechanism. Same mechanism only. When you make some defect, you can see that. The capsules block and then rupture and the healing agent comes and it's self-healed. So now here I talk about some of my own research here, what we developed here. One is about the nano container based things and then conducting polymer based one. And then a kind of 2-3 slides about some kind of corrosion sensing coatings, and finally about some super hydrophobic coatings. And these all coatings we developed in our laboratory mainly for the corrosion protection only. This is how you design a self-healing coating for active corrosion protection. So what are things you need for that? One is you need to find out first a corrosion inhibitor, that is an active agent or a self-healing material. So this can be inhibitor or a self-healing material like tung oil, or there are linseed oil. There are some publication papers, linseed oil and tung oil. They get encapsulated in urea formaldehyde microcapsules. Then you need kind of micro nano containers or capsules to encapsulate these inhibitors or active agents. So if you see what kind of capsules, the capsules can be polymeric as well as inorganic. And with the polymeric capsules, people have used especially urea formaldehyde, one of the earlier capsules formed with various sizes, 50 microns to 150 microns, 400 microns, 500 microns. And then later comes the nano capsules. Then later they found that some of the polymeric capsules does not have, they do not have actually the enough mechanical strength. So when you add these capsules inside the paint, see in the laboratory we may make in a one beaker or kind of thing, some 100 ml paints or 50 ml paints and coat. But when you make the bigger thing in the industrial level, you will have bigger reactor vessels and that get moved actually quite fast. The mixing will be quite rapid, and in that case it found that many of these capsules are rupturing very quickly. It undergo rupturing, and as such when you keep in the polymer layer itself without even mixing it, some of the polymeric bonds are rupturing and the healing agents are being released prematurely. So there are things, then later people found out they made the polymeric shell wall using a hybrid material, silica plus polyurethane kind of thing. Those things are also available now, but most of things are in the academic journals and papers only, nothing in the market as of now. And then you need to have a proper polymeric organic coating matrix of the active agent. So there are two types of encapsulation strategies. One such strategies which we made actually, you have made TAU to nanotubes and then in the nanotube and then the inhibitor molecule decide concentration and mix it under vacuum and then you do the washing and then to remove anything on top of this one. So make sure that your inhibitor is inside the container. This is one such strategy. This is known as post loading. That means you are making the nano container first and then the loading the inhibitor. Then another strategy is that in situ loading. That is, this is actually a oil and water microemulsion system. In this one, what they are getting is in the reaction vessel itself, they will have the inhibitor molecule. Here, the MBT is the inhibitor molecule, that is mercaptobenzothiazole, and then they get loaded here. So this is also a kind of porous capsules, especially silica nano capsules have been formed in this way. This is another capsules which we made in our laboratory. This is actually a hollow mesoporous zirconia capsules we made. And then starting in the non-stopper method, we made some solid silica particles. These are the, solid silica particle. And on the solid silica particle, we coated actually this this zirconium moiety we coated here. Some surfactant also used. And during calcination, what is happening is from this reaction, this bridge this surfactant is moved. So you have now the force here. Now what you are doing is doing NaOH treatment. Silicon dioxide is dissolved in NaOH, easily soluble in NaOH, so the silica will move out. So the core is removed. So a porous and mesoporous zirconia you got. So this is zirconia nanoparticle and the container size was around 400 nanometer and this thickness was, the shell thickness was 40 plus or minus 10 and this we characterized also. And later we loaded this zirconia using some MBT inhibitor. This is post loading only, and this is how you can confirm the loading. So what we will do before and after loading, we will take the UV intensity of the solution, inhibitor solution. So after loading, we found that the intensity get reduced. So assuming that the lost amount is actually inside the containers. So we found that the inhibitor efficiency was, my loading efficiency was about 63 plus or minus 2 because we duplicate all the experiments and find out the error value also here. And now, and then later we confirm that the, one has to confirm the loading of the inhibitors. So we got the signature for the 2 MBT on the hollow mesoporous zirconia. So this confirmed that the inhibitor get loaded there. And then we need to find out releasing. Okay, of course, we loaded that one, whether is it able to release or not. So one such strategy is that you use a different pH solution. So why pH means when the corrosion happens, the important thing is happening is pH changes. Anodic areas will be acidic pH, cathodic areas will be basic pH. So when the pH changes happening, this container sends that and then get released. So we found that when the pH 3 and pH 10, more amount and faster release compared to the neutral pH. So this can be based upon the releasing mechanism, maybe based upon the surface charge difference between the container and the inhibitor molecule in the acidic and alkaline environment, and the kind of electrostatic repulsion between these two, and the solubility of the inhibitor. If the inhibitor is highly soluble, means quite fast it will come. Should not happen like that. Should not. The inhibitor is not at all soluble, means cannot use the inhibitor at all, because when the electrolyte is coming inside, should able to come along with the electrolyte. So this is the container we used, and then using that container we made a coating. This is the design of the coating, and this coating is actually we applied on 9 chrome 1 moly ferritic steel. And this, the difference, both the coatings have same thickness, that means 150 micron thickness. What the difference is that in this coating, we have a nano container mixed hybrid coating is here. This is sol gel based coating only, TiO2 and silane coating here we given. And in this layer, we added this nano container. And this test is an accelerator test. This is known as neutral salt spray test. Some of you may be aware of this test. What we are doing in this test is, and you can see a cabinet here. In this cabinet, the salt solution is that is 5-8% NaCl solution. And inside this cabinet, these samples will be kept inside 45-degree vertically we kept inside, and continuously will spray the NaCl solution. And then periodically you'll observe how the sample is performing. Before putting the sample inside, we'll cut the coating and next mark as per the standard. Say ASTM standard is there, and they make the coating cutting in such a way that the surface, steel surface should be exposed. And these are the set of coating we made, and these are the after 1,000 hours. We found that in the control coating we can see I mean, the blistering happened and then it is peeled off and a lot of corrosion happened. And nanocontaminant based coating, we could able to see that only at the edges only some coating or happened. I mean, corrosion had happened. And this area is nothing happened here. And then what we did, later we found the Raman spectral analysis at the intersection here. We found the peaks are mainly coming from the iron corrosion products, mainly for the emitted characteristic peaks. And when we do the epoxy nano container coating, the coating nano containers, we found that we got some of the signature for the MPT here. That means at this, when the corrosion happening at this area, the MPT, the inhibitor molecule could reach out and stop the corrosion. So we made the mechanism based on that. So how will you propose a mechanism for that? So this is our coating that you have the alloy here, and this is a coating, and the nano container and inhibitor inside the green, dark green is the inhibitor. So if I have a defect I made here. So I have a defect here, and then in the defect, to the defect, the corrosive species can come. And at this area, when the corrosive species come, what is happening? You can see the corrosion is happening here, and that the defect mouth, the porous, it's kind of a porous corrosion products will be there, and through that, still chlorine can go, oxygen can go inside, and these are the electrochemical reactions happening here. Electrons are released and being consumed here. And when the corrosion happening, so at the anode you can see low pH. By sensing the low pH, the nano container get releasing the inhibitor and can come out and it can stop the corrosion. So if the inhibitor is coming down from here and a protective film is being formed. So this is a mechanism for a active corrosion protection for nano container based coating. So we made actually three different types of nano containers. One is silica based one. There's the mesoporous silica and the mesoporous zirconia plus TiO2. That is a nanotube, TiO2 nanotubes. And this is one part of the talk. And now we move on to the next part, that is a conducting polymer based smart coating. If you have any queries, you can ask in between also. I hope that I'm not going too fast also. Is that okay, sir? If you have any queries?
Sir, we wait 10 minutes. After that, we have to start, sir.
Sorry, sir.
Sir, we go for break, sir. 10 minutes.
Oh, no. Okay, fine, sir. Okay. So, are we breaking now, sir, for 10 minutes?
Yeah.
Okay, fine. Yeah.
Sir, we started second station, sir.
Oh, okay. Am I audible now?
Yes, sir. Audible.
Okay. So hope my screen is visible to you. The PPT is visible to
Visible,
you.
sir.
Yeah. So now the second part coming, the conducting polymer based smart coatings. So this intrinsically conducting polymers, the Nobel Prize in Chemistry 2000 was awarded jointly to three people for their discovery in 1976 by Alan J. Heeger and Alan G. McDermott and Hideki Shirakawa. So they only discovered the conducting polymers and other works they have carried out. So these conducting polymers have a lot of applications, like, in separation membranes, gas sensors, electrocatalysis, actuators, and rechargeable batteries and biosensors. They're mainly used, conducting polymers are not limited to these three, but these are the major things. One is polyaniline and polypyrrole and polythiophene. And in our talk, mainly we focus upon the polyaniline, which is we are working on these polyaniline based coatings here. So in addition to all these things, another application of this polyaniline is found in corrosion protection. So one of the unique characteristics of this type of polymer are is the ability to undergo oxidation reduction reactions by gaining or losing electrons from the surrounding environment. We know that corrosion is also playing with the losing electrons and somewhere it is being supposed to consumed. So because of this interesting feature, these ICPs have been proposed as novel anti-corrosion coatings for different metals and alloys. This is one such paper, the first paper which appeared in 1985 in the Journal of Electrochemical Society by David B. Berry. He only first who introduced the honey-based coatings of stainless steel. So he just found out that when you're modifying, applying electroactive coating on stainless steel, there is improvement in the corrosion protection in the sulfuric acid medium. So he found and the sample kept in the passive state for relatively longer period in the sulfuric acid medium when you have a coating of pani-based coating on the stainless steel. First study, and later in advanced materials in 1994, another fellow scientist, Wesley, he pointed out that ICP coatings of pani and polypyrrole possesses self-healing properties. That means in which a passive oxide layer between the metal substrate and the ICP can be spontaneously introduced at the defective site by the oxidative capability of the conducting polymer. So this that the self-healing thing is important here because then people started thinking about this ICP as a replacement for the chromate based coatings. So the research started from here. Then various combinations of pani have been introduced to various types of coating systems, both as a conversion coating as well as a pigments in the paint. Why we are using ICP? You can see that, like the chromates, the ICPs have equilibrium potential more positive than most commonly used metals. If we use aluminum, zinc, and iron, I mean, these are the most commonly used metal or metal based, these alloys based on these metals for the industrial applications. So you see the reduction potential minus 1.96 for the aluminum couple, and then for the zinc Zn2 plus couple minus 0.76 and minus 0.62 for iron. The chromalate is positive, and all the ICPs also it is positive. It's very positive with respect to the metal ions. It's varying. It depends upon the dopant or doping level and the electrolyte or the surrounding in which it is being used. So doping, I will come to that. Each conducting polymer can be doped using some kind of anions during the synthesis itself. We'll come to that next slides. So why we are using is, the idea is that introduce active agent or corrosion inhibitors into the pani as a dopant. That means you have a self-healing at the functional level, that is the anti-corrosive function. So the active agent will be inhibitor doped body, that is the inhibitor can be MBT or Q means quinoline, okay, or any other organic compound which is known as a non-corrosion inhibiting pigment. So why pani? When you synthesize, we have two form actually, salt form and base form. Generally, we will get the salt form only if you're using Cl as the acid, you get the chloride anion as the thing. Instead of phosphoric acid, if you use this synthesis, you will get the phosphate ion here. So pani phosphate you can make, pani chloride you can make, and the later people are using some organic acid also. So based on what kind of surfactants or the dopant you are using, you can dope that in this on the nitrogen here. So when you do energy for OH treatment, base treatment, the completely the dopant will go and you got the base one. The base is non-conductive. This is a conductive form. It will be generally green in color and the base form is a blue in color if it is non-conductive. So why we are going for pani? One is very easily you can produce in the lab and very low production cost and very easy to synthesize, and environmentally also it is fine, and mechanical stability and conductivity can be adjusted based upon the doping level. So how pani protecting the metal substrate? You see, these are the different kind of protection a pani can offer. First one is the barrier protection. Okay, that means a kind of a formation of an isolation film. That means the barrier when you're applying a pani based coating or a pani based film, that film is acting as a physical barrier between the metal and the electrolyte. And another one is the anodic protection. That means the formation of a passive oxide here. So here it's a protective coating against metal oxidation is the the thing which is underlying here. Each one we will see in detail in the coming slides. Then final one, due to some triggering, you can have a controlled release of some kind of corrosion inhibitors. So these corrosion inhibitors you can store in the Pani structure. And then cathodic protection through oxygen reduction reaction. So these are all the various mechanisms Pani can be used for corrosion protection. So one of the important thing is barrier protection. That is especially the conducting form, EB form, due to the high electrical resistance of a non-conducting EB form, that film can act as a physical barrier between the metal and the surrounding. So the anodic protection mechanism is the Pani acting as an oxidizing agent and for leached metal ions and maintain the metal in the passive region by providing a protective thin layer of metal oxide. The oxidation power of Pani increases with increase in conductivity. This we will see how. Actually, when you are adding Pani in the coating, this is the three steps happening during the anodic protection mechanism. So first step one, you have the coating. Okay, suppose the coating is defect free now. But now when a defect comes in the coating, so electrolyte is entering here. So what is a Fe corrosion starts? When Fe corrosion starts, Fe is giving Fe2 plus 2 electrons. So the electrons being released, the dissolution of Fe causes the cathodic shift of the potential, which initialize the reduction of Pani conducting polymer here. When we move here, it gets reduced and become Pani EB form. Okay, the stored positive charge of the oxidized salt of Pani ES can be transferred to the defect to form a passive layer here, oxide layer will form. So it's kind of an ennobling mechanism. So you can see here when the ion become Fe3 plus, the electron is coming, the electrons were used by the Pani and become 2Fe, and in presence of oxygen and water, a FeO3 film is finally formed at the defect. This is the anodic protection mechanism for the Pani. Then another one is a self-healing mechanism. Pani acting as a reservoir for releasing the doped corrosion inhibitor. So when the Pani undergo reduction, the doped anion get released, and the metal anion, metal cation will make a complex with the doped anion, and AMD complex metal, the cation anion complex will form and it form the surface. So this is one another mechanism, that is self-healing mechanism for the corrosion protection. And this is another one, that's a cathodic protection one. We'll come to that in the next slide actually. So what it doing is, this is a typical passivation curve for active passive material, the polarization curve for active passive material. Generally active Fe dissolution is happening here, then it go to the passive state, and then more than 1.2 volt means oxygen evolution will happen. Okay, so It's a passive state. In the passive state, the metal being protected. In the presence of pani, I mean, quickly the pani, the presence of pani can take the material quickly to the passive state and get protected for a longer time. That's how the pani works here. So, as I told, this is a kind of a ennobling effect due to the redox activity of the intrinsically conducting polymer, which shift the potential into a passive domain at higher potential values. And then another one is the cathode protection. How it is offering is, if I can say the oxidation power of Pani coating is greatly affected by its conductivity. If it's more conductive means its oxidation power is higher. How to make it more conducting? You can increase the dopant amount. So more passivation can be achieved by increasing the Pani coating thickness. Pani coating thickness means more amount of Pani is there. And then after longer exposure to the environment, what will happen? All the oxidized form of Pani will be reduced and finally it become EB and the conductivity decrease slowly. Regardless of this, there is a possibility that the reduced form EB can be re-oxidized by the surrounding environment. Then the electrical conductivity can be recovered again. So it's kind of a reversible process, cyclic process. So what is happening in the presence of when the oxygen reduction is happening, more than 1.2 volt is happening now, electrons are coming, right? The electron will be taken back from the Pani EB and it gets reoxidized into the conducting form, that is ES form. Again, it can do the ennobling mechanism. So it's a continuous process. So a proper self-healing can be provided by Pani as an ingredient in a coating. So this is the idea, and in the lab we made some of the coatings. Actually, this work we work for the Boeing USA. They want to make a coating for the aircraft material, the aluminum alloy AA2024 alloy. So this is a Pani-based self-healing primer we formed, and then we did the work, and we able to have a pattern also with joint pattern with the Boeing. So this is the Pani synthesized method. Okay, you can see the green color, that means the conducting Pani have been formed. This is the reactor facility available with us. With this, we can make more than 100 grams of Pani in one synthesis itself. We can make, and then we'll do all those doping and de-doping and whatever. In the de-doped Pani, you can add any type of dopant and dop it again, and the desired thing you can make. And then the coating we made, and this is the pigment, including the Pani pigment. In a typical coating, we'll have many other pigments also. And I don't know how many of you are into the paint formulation. So, for example, for a paint formulator, there are some values will be there, like the volume solid and pigment volume concentration. Simply, I would say that the volume solid is the total solid content of the coating. That means 75 the volume solid means remaining 25 is solvent. Okay. And the pigment volume concentration is what is the concentration of the pigment in the volume solid, that we fix as 20 only. Sometimes you cannot increase it more. 30 means that we called there will be a critical pigment volume concentration. If you surpass that, the critical pigment volume concentration, the resin, what is the paint, cannot hold the pigment. When it crack there itself, then there will not be any barrier property. So this is what we mix the pigment first by adding the resin and the solvents, and then we are spray coating it. So these are the different ingredients added here. So these are the araldite GY 250 is the resin, and this is the hardener. It's an epoxy system, two-pack epoxy system, 2:1 ratio. We mixed it, and the reaction happened. And then finally we got the coating. This is the coated sample. Then we have tested called the SAR spread testing and all those things. So these are to find out what is the barrier property of the coating. A blank coating, and this is the Pani phosphate and Pani MBT. We actually developed various other formulation also using various benzoate, Pani benzoate or Pani quinoline and Pani hydroxyquinoline. We used various things we used, but here we are showing only three things only right now. So after almost 2 months, 1440 hours, this was inside the SAR spray chamber, and we found that more blisters were there in the blank coating, but when the Pani was there, the blisters were less actually. And then the most important thing is the coating can act as a self-healing or not. So I will go into that in the another slide here. So this is the one instrument we have in our laboratory, that is the SVET instrument, that is scanning vibrating electrode technique. So what we are doing here is, so this is the coated specimen. We mounted it on a, epoxy resin here. So what we'll do then, this one, you can see here where the pointer is that this is the bare one. That means there is no panning here, and this is the panny one here. Okay. So what we'll do, we will make actually small defect. You can see a small defect here. The defect we'll make on the coating, and then that this is the where the sample has to get the specimen. This is in the more enlarged view. You can see this is a sample here, and you can see in this here the tip is the mic the probe is here. The with the uncoated conductive tip will be there. The size of the tip will be 5 to 10 micron, and so that will be the sensitivity of the tip also. So what the tip is doing using the piezoelectric driver here, it can move XY direction and Z direction. So it will move Z direction, and then like this, like this, like this, it will move. It will scan a small area and it will find out what is the potential difference across it or the current it can map. From the current, one can say about whether what's the corrosion is happening it or not. So when you make a small defect on the coating, the defect will make in such a way that the metal surface is exposed. So we are making corrosion to happen there and see whether the coating can stop the corrosion after some time. So this is a blank coating. That means here we don't have any type of inhibitors here. There is no pani here. So I made a defect here. You can find out that from the defect I'm getting a peak. So this is the anodic activity. And after 6 hours mapping the surface, I found many areas anodic peaks are coming, and this peak is not being reduced also. From 24 hours, we can see the surface is freely corroding. There is no active corrosion protection. Various other phases you can see, able to see some kind of anodic activity and cathodic activity also getting increased. When we add the Pani phosphate, this is defect we made here. We can see the current is here. The peak is coming here. And another thing, the current value is in nanoampere only, but here it is a microampere. So that itself shows that lesser corrosion activity only. But after 21 hours, we saw the peak is completely healed. And then Pani MBT is also peak is healed. That means when you're adding this inhibitor here, the Pani-based inhibitor here, it can heal the defect here to the self-healing mechanism. So further, we did a dedopt one also. The dedopt one Pani, we put a defect here, but the dedopt case, it is only able to give barrier protection. It is not able to give any kind of active protection. That is why there is no diminishing of the peak here. Okay, but at the same time, up to 60 hours we tried, but there is no diminishing of the peak. At the same time, we can say that when you're adding Pani dedoped also, the current, the value we are getting in nanoamperes only, not the microamperes compared to that of the blank. So we can say it's able to give better protection as well as self-healing ability. And then there is another one, as I told, this Pani can be added into a zinc-rich coating also. So this is a typical traditional coating system. The zinc-rich primer is there. The zinc-rich primer only we are adding the Pani-based pigments and find out how it is working. So I'm not going to give much details here. Same, I will show some of the results here now. You can see this is a salt spray coating. Salt spray of results of the coating after 6,000 hours of salt spray test. So these are the coatings actually with different amount of Pani pigments added. See, you can see very little amount only we added, 2% only added. This coating is IZP, that is without adding any pigment. We can say the rust marks, of course, the white rust is nothing but from the zinc only, but red rust you can see here. This kind of red rust mark was not seen here. So this coating actually we developed for the IOCL, and right now these at the field trial in IOCL almost 9 months over yet to see any kind of corrosion spot on this type of coating. And then another thing, now we finished that conducting polymer part, we'll move on to another thing, that is a corrosion sensing. So we all know that corrosion is typically characterized by a reaction of two parts. That is one anodic part, that is oxidation part, another cathodic part. So with the onset of corrosion, what are changes happening? The pH increases in the local cathodic areas due to the formation of hydroxyl ions. Acidification at the anodic site as a result of the hydrolysis reactions, H plus ions are coming there. So local anode and cathodic site will be formed here. And respective pH variation can be used to detect and locate active corrosion spots on the protective layer. Suppose you are applying a coating and kept as such, maybe underlying corrosion is happening, but it will be visible to you when you are able to see a corrosion product visibly by red rust mark in the case of iron, or a white corrosion product in the case of aluminum or zinc. Otherwise, you can't see that. In the magnesium, you can see dark colored. I mean, corrosion products. Otherwise, you cannot visualize this, or the coating has to peel off. So this, what we did is actually we made some silica nanocapsules, and we add some indicator here. Phenolphthalein is, we know, the indicator which can sense, it turn colorless to pink when alkaline environment comes. So we loaded this thing inside the containers, and then these are the container. Actually, what we did is we made container, we drop casted on a glass light to check whether it is able to clean the car or not. We put a drop of, Na oil solution here, immediately change the color to pink. So the container can sense it. So that means through the container, the indicator is releasing. Then what we did, we made a coating, a PDMS based coating based on this container. Then again, we put a drop here. We found that where the drop is put, the color is changing. That means this, it is working when you are putting in the coating. And then what we made is applied over a magnesium alloy, the same coating. Then we made a scratch here. So we can find out that at the scratched area, some area the corrosion is happening, other areas the pure coloration is happening. That means all catalytic reaction is happening all over here. The corrosion is starting somewhere. So this is a showing example that the pH sensing ability of these silica-based nanocontainers can tell that corrosion is happening somewhere. So you need to see that and remove that coating that area and do the patch-up work. So this is a simple mechanism, and damage is coming. The corrosion is happening. Then the OH minus buildup is there. Alkaline pH is coming. Sensing the alkaline pH, the indicator molecule, the phenolphthalein is releasing, and the color change is happening. And that's the response of the coating. So this way we complete here this part also. Now comes the last part, that is a kind of super hydrophobic coating. So we can, based upon the wettability of the surface, we can classify surface as hydrophilic, hydrophobic, and super hydrophobic. So we see that when the contact angle, when the water is here, the angle here, contact angle, if 0 means the perfectivity, in between 90 and 0, high wettability, between 90 and 190, low wettability, and equal to 190, perfectly wetty. So is called as a surface is hydrophobic when the contact angle is more than 90 degree. When the water contact angle is more than 150 degree, we'll call it as a super hydrophobic coating. So in our lab, actually, we made a kind of, electrochemical fabrication for a super hydrophobic coating for aluminum alloy. What we did is anodize the aluminum surface using a TSA method. Then we electro deposited some compound here to make it as a super hydrophobic. This was a more fundamental work only. What we want to know is there are reports already using cerium stearate based coatings. So we want to study at what potential and how long you should do the deposition to get the maximum coverage. And we want to fundamentally know because cerium we are adding cerium 3 plus, that's a non-corrosion inhibitor for aluminum. So what is the synergy between the super hydrophobicity and the cerium 3 plus, the active corrosion protection, how good it is? So these are the photographic image you can see here. This is the uncoated sample, not uncoated. This is a 1 minute we deposited, and it is water contact angle is 102 only. That means it's hydrophobic but not super hydrophobic. There is no rolling off. But as we increase the deposition time, the contact angle increases. You can see 120 minutes. This is surface how looks through FEC image and how a water droplets is sitting on the coated surface. And we found that as it get increasing up to 120, we are able to get the super hydrophobic regime and complete coverage of the surface. But from we increase to 180 degree, 180 minutes we increased, we found that slight decrease in the contact angle. So we see when the FEC images we found, there is an anodized image, anodized aluminum surface image. Within 1 minute, we see that some kind of nucleation is happening, but there is no growth of the layer. And then 10 minutes in some area it started growing, but there is no proper structure here, but there are many places uncovered. You can see now from the 30-minute onwards, you're able to see some kind of, structure is particle is getting grown on the surface, but still it is not covered. And 60 minutes also it is not covered. And on 120 it is completely covered and secondary growth also started. 180 what is happening, the high potential and the more time for the deposition process, a kind of charging happening. That is why the contact angle get decreased also. When you enlarge this area, we able to find that the single almost 1 micron size will be the for each kind of spears. And then the on each one structure, if you see here, a rice husk structure you can see on top of it, kind of a micro nano texture, because on a micro particle here, I can say I'm able to create a kind of a nano structure. So this micro nano texture is going to give you the super hydrophobicity, because when the water molecule is sitting on these type of surfaces, the water molecule is not exactly sitting on that surface. Instead of that, the air trap in between these kind of grooves, a typical lotus leaf effect. And this is the AF image of that type of coating deposited at various time interval. And as you can see that the contact angle is getting increased, the electrode response time is increasing, and the roughness also increasing. This is the, we did the corrosion studies also for these coatings. And I will explain this part, especially the SPEP part. And this is the uh, without any coating the anodized surface. If I do the anodized surface, if I do the SPT mapping, you can see that at various places the anodic activity is happening, cathodic activity is happening. The red color is actually represents the anodic activity. The blue color represents the cathodic activity. The green color, the electrochemically not active neutral area. Okay. And then as the time increases, I can see that more or less it is some area it is stopped and other area it is increasing, and everywhere it is happening, and the cathodic peak is also higher. So it's a fully corroding condition. But in the case of cerium doped one, I mean the cerium stearate electrodepositor coating, I could able to see some of the anodic peak initially. The corrosion is happening initially, and 12 hours it get increased. 24 hours, I could see that this completely stopped here. Electrochemically neutral areas emerged up to 48 hours. So a kind of self-healing or active corrosion protection is offered by the cerium stearate also, in addition to the super hydrophobicity. For the improved corrosion protection we observed from the dynamic polarization studies and electrochemical impedance studies. And then if you develop this kind of coatings, we should find out the mechanical stability. What we did is we actually rubbed the surface using a silicon carbide paper using a 50 gram. This is a standard test we used to do for these kind of coatings. They found that if the abrasion length wants, the contact angle value get decreased. So it is still in the hydrophobic range only. Environmental stability, we found the contact angle for almost 1 month in the NaCl solution, and we found that it getting decreasing only, but it's still in the hydrophobic regime only. And then the ambient air UV stability, it is very good up to 1 month. And then the self-cleaning ability, that means some dust we are keeping here, then the water is dropping here, it's rolling off, and while the water is rolling off, it is carrying all the dust also with that, and it is being removed also. There is one another coating, that is the epoxy siloxane nano composite coating we prepared, and this also showing super hydrophobicity. So this is various combination we made actually, like this also one pattern we applied for this one, and this epoxy siloxane coating various we added various pigments here to impart the super hydrophobic function. I will show you one video here how this coating is really working. This is uncoated surface. The how it is happening. And the metal surface, when we are pouring the water, I mean, it is freely rolling off here. And then this wooden surface also being coated using the same thing. You can see it is bouncing off and it's on the concrete substrate. And another recent thing what we are working over is a volumetric superhydrophobic coating. That means lab actually accidentally when we prepare a similar type of formulation, we got two types of coating. One is having a petal effect, that is a rose effect, and another is the lotus effect. So here we can see the rolling of phosphor in the lotus effect sample, but in the rose effect sample, petal effect sample, there is no rolling of because surface is having very high adhesion, but the water molecule is able to sitting there. But even if we keeping the substrate upside down, molecule is still adhered to that. Super hydrophobic regime only. It is a quasi state. It is a quasi state because it is water molecule is sitting on the air molecule here, but here there is no air molecule here. The water molecule able to penetrate through the grooves on the surface. Here the water molecule cannot be able to penetrate here because presence of air here. This is the coating we made, and this is a FEC image and the AFM image of the coating we made, and this is the photographic image of the coating. So why we are calling it as a volumetric? Because throughout the coating is super hydrophobic. Throughout means throughout the volume of the coating. That means when you scratch the coating, here I am scratching the coating using emery paper, and I found that still it is having the water contact angle quite high. So it is still even it is increasing actually after scratching. So it is the depth of the coating also, it is super hydrophobic with the presence of the pigments we added in the coating. And we have done some impedance analysis also for the both the coatings. You can see the initially the both the coatings have very high impedance value. Generally, if the impedance value is higher than 10 raised to 6, we say it's a very good corrosion protection, but superior and excellent one can classify when it is the value is higher than 10 raised to 10. Here we found that the corrosion products appear on the exposed area after day 14 in the case of a hydrophobic coating. In the case of a super hydrophobic coating, up to 32, it is having very high corrosion protection. During the 36th day, we found that it getting reduced, but there was no corrosion products. So we can say that the PDMS based coatings will have a lot of pores. So through the pores, actually the oxygen can go inside and undergo kind of oxidation and corrosion may be started there. That is why the decrease we got. But still we couldn't find any kind of corrosion products here. This work is in progress right now. So to come to the summary of this talk so far, what I've given, especially the for self-healing coating, I can say that this is a promising technology to provide the active corrosion protection, but not sure the complete recovery of the physical barrier property. This is the biggest question mark. Recently one paper published in Progress of Organic Coatings in 2020-21 saying that when you're adding the polymeric nano capsules, yes, of course, it is able to give you the active corrosion protection, but it is compromising the barrier protection. That barrier protection is more important for a coating protection is concerned. So the active protection should come into play only when the barrier property is having some problem or it is under threat. But generally, for the addition of the active ingredient should not affect the barrier property. So there are some problem with that. Many of the coatings developed are good only on the paper, reality, not useful for industrial application. If you see these type of coating is in the market right now in India. There's nothing in the market, I would say, but there are coatings are available in the USA. It is available, especially PPG, one coating manufacturer. They have the technology, and they collaborate with the NASA and one other institute. They have the technology. So the three people participated in that. One company they made the pigment, and then the paint made by the PPG, and they collaborated. Then that came even after research of almost 10-20 years, that coating is coming up, but still there is a lot of problems with that. Industry yet to accept that kind of coating as a replacement of zinc rich one, and the cost is also another aspect for that. And the long-term efficacy of the corrosion inhibitors inside the coating matrix is also not clear still. And another thing is the nanopigments. We know that the nanopigments are good, but the dispersion is another big problem. When it is not properly dispersed in the coating while application time, it can affect the barrier property very seriously. Another thing you see at the defect site on the coating, there will be competition between the large corrosion inhibiting molecules and corrosive molecules such as H2O2 and chloride minus ions. They are small. When the competition between the smaller one will have the more agility and they can come quickly there and can start the corrosion. And further, the challenge is to preserve the desirable properties of the coatings to achieve effective self-healing with minimum loading of nano containers or microcapsules. So now the research is happening in this direction as far as self-healing coating is concerned. And if you go back to the super hydrophobic coating, the problem so far in the market, for the architectural coating, there are hydrophobic coatings are available. But as far as super hydrophobic coatings are concerned, for the industrial coating, nothing is available in the market as of now, except a coating offering from the Hempel. But again, the long-term durability of the super hydrophobic nature is in question. And what about the chemical and environmental stability of the coating? And what about the abrasion resistance? And there are need to develop a self-healing superhydrophobic coating. So these are all the researches right now happening in the superhydrophobic coating field. So with this, I will conclude my talk. I hope I could able to complete in time and we can have discussion based on this work. And thank you. And this is image belongs to one of Chitnad Manson here in Karaikudi. If anyone near to came to Karaikudi might have seen, or you can visit my institute and these areas in and around Karaikudi also. Thank you for listening my talk. And now if you have any query, you can ask.
Thank you very much, sir, for your wonderful session. Participant, please, any queries to the speaker?
Think I've seen some messages there, but I couldn't able to see that messages. I mean, in the chat box, please.
So there's a question in chat box.
Yeah.
What are the difference between organic coating and green coating?
Yeah. I mean, most of the organic coating, I don't know what exactly thinking about the green coating. A coating can be green, I can say, when you are decreasing the amount of solvent in the coating. For example, another is two types of coating. One can say one is a solvent-borne coating and water-borne coating. Most of the water-borne coatings are one can say green coating. That means one thing you can use a water as a solvent instead of the xylene or toluene or MIBK or any others as a solvents. So there itself you have some kind of green thing added to the coating, and water-based acrylic coatings are available, water-based polyurethane, epoxy coatings, all these things are available. At the same time, there are problem with these things because not able to match the protective property given by the synthetic organic coating. And then you can make a complete organic coating by removing all these epoxy resins and polyurethane, all other resins which are organic, the chemical synthetic molecules. Instead of that, you can go for a naturally occurring ingredients can be used and you can synthesize such kind of resins and can used for the coating. But the problem is that for industrially, you can't get that protection point of view. This coating can't touch these epoxy and other coatings. So the coating industry or the research currently moving towards replacing the solvents. So increase the amount of the solid content in the coating. That means 100% epoxy coating, 100% polyurethane coating, and avoid the solvent part, because the solvent only being always released and creating these, emissions. Is that clear? And nowadays, nanoparticles or nano emulsions are coated on fruits, safe for consumption. Okay. The thing is that many of these, the toxicity of the nanoparticles are in question only, because even TaO2 also, because TaO2 is one such pigment. Without that, the paint cannot sustain, because TaO2 the unavoidable thing. But the nano regime, the TiO2, the toxicity for the cellular level, all those things, still a lot of studies are going on. And then regulatory team only should comment about that this can used or cannot be used. At the same time, I would say that there are food grade epoxy, because when we visit, for example, here near our Karaikudi, one area called Tirumayam. In Tirumayam, actually, there is a factory for the Murugappa group, and they made the Paris, under the Paris brand, various sugar they are making, and all those things they are making there. So all their plants undergoing corrosion. Okay, so the coating they are giving for the plant and various structures, equipments, are food grade epoxies are there. So it will not contaminate the food. It will not leach out those things to the food. So food grade epoxies are available, and some of the tins also will coated with the food grade epoxies. So, but consumption, all those things, you wash and use it, but we can't say the nano level. Most of these big particles, I mean, these materials, how they function, yet to know actually. So any other questions, sir?
Say any question, participant? So this is for a digital movement to you.
Okay, thank you, sir. And further, if anybody interested to work on corrosion or coatings, you are free to contact me in our lab, or we can collaborate and we can work also. If anybody interested,